Okay, here on example 4, we want to try to solve an exponential inequality by using logarithms. The fact that it's an inequality doesn't really add anything to it. Could have just as well been an equality. However, we're going to go through the steps and see how we would manipulate this kind of expression to get down to a solution. So first of all, we get the original inequality that 6 raised to the 2y minus 5 power is less than 5 raised to the 3y power. So in the end, we're going to get that y is got to be greater than some value for this inequality to work. Y will have to be greater than some value, and you can jump ahead and see what the answer is here. Now, how do we get to that answer? Well, we just kind of do the typical steps that we're used to. So first of all, we use our nifty product of logarithms that allows us to move these values out of the exponent. So first we do our log of both sides. Right, so we apply that log function to both sides to get here. Okay, that's the property of inequality for logarithmic functions. Just means that if you have things that are in an inequality, then we can apply the log function to both sides. It's just kind of an operation that we can do in a balanced way to both sides. The power property of logarithms that's being referred to here is bringing this power down. So we can say 2y minus 5 times log of 6 is less than 3y times log of 5. Okay, at this stage, we're just going to use the distributive property over here so that we'll get 2y log 6 minus 5 log 6. Okay, at this stage, if you're kind of keeping track of things, this part would be some constant value. This part still has a variable in it, so that's the variable that we're going to need to get by itself at some point. We'll keep 3y log 5 on the right side. We can subtract 2y log 6 from both sides to get all of the y's on the same side. So we're going to subtract this whole thing off of the left side, and we're going to subtract that much from the right side. So we are going to have negative 5 log 6 remaining on the left, and on the right we'll have 3y log 5 minus 2y log 6. At this stage, what we can pull out is going to be, we're going to use the distributive property here and pull out kind of a common factor. So I think we are able to just pull out the y, I believe. So what that would look like is, let's make this full screen so we don't have to have such bad handwriting. Left side will stay the same. On the right side, I'll have y pulled out, and we'll have 3 log 5 minus 2 log 6. Okay, I'm pulling out that y because it's just a factor in each of these two terms, right? We have 3 times y times the log of 5 minus 2 times y times the log of 6. Y is a factor in each one, so we can pull that factor out. Finally, we can divide by all this stuff to get rid of it. So we can divide by 3 log 5 minus 2 log 6. And our final solution is negative 5 log 6 over 3 log 5 minus 2 log 6. And we would take that into a calculator and very carefully find the value for each of these 3 terms, simplify it down. And if we went through those steps, what we would get as a solution would be negative 7.19. So that'd be our solution. Now, there's a portion below that that says test that is going to work. Test that this solution is right by putting in a value that is greater than negative 7.19. So this is saying that this inequality is true whenever y is greater than negative 7.19. So if we put in like negative 7 or negative 6 or negative 5 or negative 4 or negative 3, anything bigger, if we put in any of those values here, what this simplifies down to should be a true inequality. So they suggest testing y equals 0. Now, why should we do that? Well, because it just kind of simplifies things the fastest. So if we put in a 0 for y, right, 0 is greater than -7, then on the right side, we have 3 times 0. So we have 5 to the 0th power. Well, that's just 1. So that side simplifies real quick. On the left side, we get 0 minus 5. So this one is what we'd have to put into a calculator or just write out by hand. You could say, well, we'd know that this is less than 1, right? Because this is just going to be 1 over 6 to the 5th power. So a 6 times itself 5 times. That's just going to be a very, very small answer in the end. It's going to be less than 1. So it's going to be true. And that would be a test of our solution that said that y should be larger than -7.19. So if we went through those steps and put in -7.2, if we put in -7.2 for these y values, we'd get some statement where on the left side, we actually had something greater than 1, and it would not be a correct test because we'd not be using a correct value. Okay, in the next video, we're going to go over the change of base formula. The change of base formula is a formula by which you can change from base 10 into any other base you want to work with. So base 10 is our kind of like baseline logarithmic kind of reference point. We can do base 11, we can do base 9, we can do bases with decimals. We can do any kind of bases we want because we can do any kind of exponents we want. So for any given exponential equation, we're not likely to want to use only base 10. We may want to use different bases to kind of deconstruct different kind of exponents. Later on, like next week, we're going to talk about a base for doing the e function. So when you have like e to the x, there's a certain base for that, and that's one that is very, very, very common in use in calculus and statistics. It's basically the one that you'd go to almost every time. But the way that this gets done, the way that this formula gets proven anyways, is shown pretty well by a Khan Academy video, so I'm not going to do that one myself. I'm just going to link to a Khan Academy video for you guys to watch next, but they will go through and they will show why it is that you can take some base and change it to a new base by using this formula. Okay, so in the next video, you can watch that from Sal Khan and get a good explanation for how that change of base formula comes about, where it comes from. And then in the following video, we'll work with that in order to try to evaluate some non-common bases.